Let's introduce a family of random variables for pairs of random variables. So this is going to be our most important family when we're dealing with multiple random variables, and it's jointly Gaussian random variables. To start, we're going to need a building block. So we'll say that u and v are independent standard Gaussian random variables. If u is Gaussian with mean 0 and variance 1, v is also Gaussian with mean 0 and variance 1, and u and v are independent random variables. Their means are just going to be 0 and 0. Their variances are going to be 1 and 1. Their covariance is going to be 0 because they're independent. Their marginal PDFs are just going to be individual Gaussian PDFs with mean 0 and variance 1. So we've written that out here. And finally, since they're independent, the joint PDF we can just get by taking the product of the marginals, like this. And we can write it as 1 over 2 pi e to the minus 1/2 u squared plus v squared. And overall, we get a contour plot that looks like this. It's circularly symmetric about the origin. It's basically like a hill that has a peak centered at 0, 0 and falls off exponentially from there. Okay, so what is a jointly Gaussian random variable? Well, x and y are jointly Gaussian random variables if we can express them as linear functions of some independent standard Gaussian random variables. So that's the easiest definition to keep in mind. So if we can write AU BV plus C for x and DU EV plus F for y. So those are linear functions of two standard Gaussian random variables u and v. Then we'll say that x and y are jointly Gaussian. But we usually don't use this linear transformation as the way to specify the random variables. That's just something hiding underneath. We usually specify the distribution with 5 parameters. So usually we would just give the means. So we'd give mu x, which is the mean of x, and mu y, which is the mean of y. The variances, sigma x squared, which is the variance of x, and sigma y squared, which is the variance of y. And then either the covariance or the correlation coefficient, which is just the covariance divided by the square root of the product of the variances. So either of these suffices because from the covariance you can get the correlation coefficient, and from the correlation coefficient you can get the covariance. So what this means is that we're usually leaving the linear function implicit. So there's a linear function that's specified by the a, b, c, d, e, f coefficients, but we usually don't give that. We usually just give these 5 parameters. The most important property of jointly Gaussian random variables that we can see immediately from here is that linear functions of jointly Gaussian random variables are themselves going to be jointly Gaussian random variables. Okay, and why is that the case? Well, we can see it visually. If I have uv and I take a linear transform, so 2 linear functions to get x and y, then I take another linear transform to get w and z, well, I can just write this end-to-end as a single linear transform, and that's the definition of a jointly Gaussian random variable. There's a linear transform carrying the standard Gaussians u and v to w and z. Okay, so all we have to do then is update the parameters. All right, so what we have are the means, the variances, and the covariance. And we can just use linearity of expectation and the variance and covariance of linear functions to update these parameters. We don't have to do anything with the PDF directly. And you'll see why we want to avoid that. The joint PDF is actually a bit unwieldy, and we don't expect you to memorize it. So I'm just going to write it out so we see it. It's a long expression. It's going to take up this whole line. It has this constant up front, which involves the standard deviations and the correlation coefficient. Here's something that's similar to that 1 over 2, but now we have the correlation coefficient. And then I have this term in the middle that varies, and this is just an ellipse, just a particular ellipse. Okay, and we're going to see how each of these parameters, the mean mu x, the mean mu y, so that's the mean of y, the variance sigma x squared of x, sigma y squared, that's the variance of y, and finally the correlation coefficient of x and y, we're going to see how all of these influence the contour plot. But first, I want to emphasize that you do not need to memorize this formula. All you need to remember is that this is a formula or a distribution that's fully specified by the means, the variances, and either the covariance or the correlation coefficient. And if you have those 5 numbers, that's enough. All right, so let's try to get some intuition though. So instead of just staring at this formula, let's try to see how each parameter influences the contour plot. Let's start with the means. So changing the mean, mu x, shifts the distribution along the x-axis. It's very intuitive. That's what we're used to seeing. We'll see the same thing with changing the mean, mu y. So if we change mu of y, that also shifts the distribution along the y-axis. Right? So let's just look at a visual example. What we're going to do is fix the variances to 1 and fix the covariance to 0. So I'm going to start with this plot that I had in the beginning at 0, 0. So this plot on the left is the exact same plot we had at the very beginning for standard Gaussians, except I've zoomed out a little bit, so I have room to see things shift around. Now I've shifted it by 2 along the x-axis, here by -3 on the y-axis, and here by 2x and -3 on y. And you can see that in each case, it moved as you expected it to. It went to the right, then it went down, and then it went down to the right. Okay, what about the variance? So changing the variance, or rather increasing the variance sigma x squared, stretches the distribution along the x-axis. And if I increase the variance of y, so sigma y squared, then I'm going to stretch the distribution along the y-axis. All right, and I can change both of them and get stretching along both. So as an example, now let's hold the means fixed to 0. Let's hold the covariance again to 0. And we'll start again with our basic plot with variances 1. Then we'll increase along the x-axis and see the stretch, along the y-axis to see the stretch, and then both. We see that both axes are stretched out. Finally, let's look how the correlation coefficient influences the distribution. So changing rho x means increasing it towards 1. And what that does is it squeezes the distribution along a particular line, which is sigma y over sigma x, x minus its mean plus the mean of y. This particular line isn't that important. You don't need to remember this. We won't really use it. It's just if you want to help visualizing where things are going, it is this line, but this won't really play a major role for us. Similarly, for negative rho, decreasing rho xy towards -1 squeezes the distribution. The line is the same, except now it has a negative slope. Okay, and the same thing is true if you change the covariance, because covariance and correlation coefficient are just scaled versions of each other. And it would just be that you're increasing the covariance or decreasing it towards something that looks like sigma x, sigma y. But that's not too important. So as an example, let's first fix the means to 0, the variances to 1, and we're going to start changing the correlation coefficient. So starting at 0, then 0.5, and then 0.95. And you can see it is getting squeezed along a particular line. So it's continually getting squeezed. Let's look at now if the means are different and the variances are different. So now x has variance 4, and I look at 0, minus 0.5, and minus 0.95. So I see that it got squeezed again along this line of negative slope. And finally, let's try to understand where this line was. So the line was 1 over 1 times x minus 0 plus 0. So here it was just y equals x. And you see that fits perfectly. That's where we were getting squeezed. In the next case, the line was y equals minus 1/2, then with some constant. So overall is minus x over 2 minus 5/2. And you can see that that line also fits well. Okay, finally, what are the properties of jointly Gaussian x and y? Well, there are actually a lot of important properties. I'm just naming some basic ones for you, but jointly Gaussian random variables show up in all sorts of applications in engineering, data science, machine learning, And as you encounter them in different contexts, you'll learn more properties. But here are some of the most important ones. So if you have linear functions of your jointly Gaussian random variables, so w and z are these linear functions, then we know from earlier that w and z are jointly Gaussian with parameters mu w, mu z, sigma squared w, sigma squared z, and the covariance of wz. And you can get these parameters using the linear of expectation and the variance and covariance of linear functions formulas. So those are available in a previous video. The marginal PDFs are Gaussian, okay? And they're Gaussian with means given by mu and sigma squared. The conditional PDF of x given y is also Gaussian, okay? Where the conditional mean is this formula, mu x plus covariance of xy over the variance of y, y minus its mean. And that could also be written as mu x plus rho xy, sigma x over sigma y, y minus its mean. This particular formula will show up in an important context later. So this will turn out to be really important for estimation and inference. And we'll see that a bit later. And the conditional variance in this case turns out to not depend on y, the specific value of y. So what I mean by that is it just looks like this. It's just the variance of x minus the covariance squared over the variance of y, or sigma x squared minus rho squared. Those are equivalent formulas. Okay, so that gives you the conditional PDF of x given y. You could derive the same thing for y given x, just switching the roles of x and y. Finally, another strange thing about Gaussians is that uncorrelatedness implies independence and vice versa. And what's strange about this is that, well, uncorrelatedness is just this being zero. What's strange is that usually this direction does not hold. So if I just told you I have a pair of random variables and they're uncorrelated, you cannot infer they're independent without more information. Whereas if I told you they're independent, you can always assume that they're uncorrelated. Jointly Gaussian random variables are special because their uncorrelatedness automatically yields independence.